Hello everyone, I am Samarth Bofle. Today I am presenting my project titled Design and Implementation of an Automated Big Data Analytics Pipeline for Environmental and Urban Infrastructure Insights. This project was done as a part of my MSc in Data Analytics and focuses on Ireland in 2023. The key idea here is not just analyzing data, but building a full end-to-end big data pipeline using tools like Apache Spark, S3 compatible cloud storage, fast API, and Streamlit, similar to how real world data platforms are built. Problem, motiv- Problem motivation. The motivation for this project comes from a very real issue. Environmental risk is never caused by a single dataset. It is multi-factor. Weather patterns like rainfall, storms, and wind directly stress urban wastewater infrastructure, especially in cities. The problem is that although public datasets exist, they are fragmented, heterogeneous, and not analytics ready. Most student projects stop at running a few an analysis in notebook. In this project, I deliberately focused on building a reproducible automated pipeline, not just chart. Research objectives. This were the core objectives of the project. First, to automatically inject heterogeneous environmental data, not manually download files. Second, to process data at scale using a distributed computing, which is why Spark was used. Third, to derive meaningful compliance and risk indicators, not just descriptive statistics. Fourth, to store outputs in the analytics ready format like Perquit. And finally, to deliver result through an API and interactive dashboard, creating analytics as a product, not just an assignment. Dataset used. This project used two complementary datasets. Dataset A is weather data from the Open Meteo API covering data daily weather for Ireland in 2023. It includes temperature, rainfall, wet days, and wind speed. Dataset B is EPA urban wastewater infrastructure data which contain compliance status, treatment type, population equivalent, and plant design capacity. The reason this pairing works is that weather provides time series context while wastewater data provides infrastructure capacity and compliance context. Together, they allow operational insights, not isolated analysis. System architecture. In this slide, you can see the entire system architecture. At the top, we ingest weather data via API call, EPA data via file loading. Both datasets are first stored in Wasabi object storage, which is S3 compatible. From there, Apache Spark performs cleaning, normalization, feature engineering, aggregation, and risk analysis. The process output are stored as a Perquet files. These output are then served through a fast API REST service and finally visualized using a streamlined dashboard. This raw processed analysis separation is intentional and the follow industry best practices. Big data processing strategy. This slide explains how the data is actually processed. Apache Spark is used for distributed ETL, which means the system can scale beyond a single machine. The pipeline performs schema normalization, data cleaning, wait day indicator creation, monthly aggregations, and capacity versus load comparison. Perquit is used because it is a columnar format which improves the performance and makes downstream analytics faster and cleaner. Risk, compliance, and logic. This slide is very important because it's explain how insights are derived, not just displayed. Wastewater systems are first categorized by compliance status, pass, fail, or unknown. Then a derived feature called under design is calculated when population load is greater than plant design capacity. A rule-based risk flag is created when a system fails compliance and is under design. This logic allows the system to produce or prioritize a wastewater risk hotspot rather than just showing a raw table or chart. Result overview. In this slide, you can see the key result produced by the pipeline. For weather, 365 days of data were processed. Total rainfall was 1076.8 mm. There were 267 wet days for wastewater infrastructure. Most systems passed compliance, but 14 systems failed. Several high-load, under-designed urban areas were identified. These results confirm that the pipeline works end-to-end and produces interpretable outputs. Automation and dashboard explanation. This slide focuses on delivery and automation. The pipeline runs in a batch-driven manner, meaning the same process can be rerun without manual step. Outputs are exposed using a fast API REST end output end endpoints, which makes the data reusable. Now looking at the Streamline dashboard, in this screenshot, you can see high-level KPIs at the top, monthly weather trends, weather water compliance, breakdown, and a risk hotspot table. Filter allows user to focus only on failed and under-designed system, which is useful for design making. This makes a pipeline interactive, not static. Limitations and future work. To conclude, I want to be honest about the limitations. This project does not use a full orchestral tool like Airflow or Prefect. Spatial analysis is limited, even though a geometric exists, and the analysis focuses on a single year. Future work would include a multi-year ingestion, schedule, workflows, and spatial risk mapping, stronger validation and monitoring. However, the core pipeline design is solid and extensible, which was the primary goal. Thank you.